So, hey everyone, let me know if you can see my screen. I believe so. It's showing the database internals meetup, and I'm today's host, Masaka. So, we are going to cover chapter 5 of database internals book, and the chapter name is Transaction, Processing, and Recovery. And I'm going to cover the first half of this chapter. And the reason for that, I found it's a little bit hard to give an overview of everything that's happened in this chapter within an hour. It's just impractical because it covers the buffer management, it covers the crash recovery algorithms and concurrency control algorithms, which any of the individual component can take maybe 2 hours, 3 hours to talk about them. So I split them into 2 weeks. So next week, I'm going to talk about the concurrency control part of this chapter. And this week, I'm going to talk about the first half, which has the buffer management and recovery. All right, before we begin, again, we have the policy against harassment here. Okay, so let's get started. In the meantime, if you have any questions or any comments on the contents, feel free to just unmute yourself or just type the comments on the chat. I can see everything in the chat, so that's also fine to me. So last time, Verity gave a kind of overview of the chapter 4, implementing B trees, and that chapter just has loads of information about the tricks you can do in B tree to kind of improve your performance and reduce the size of the disks. So they covered page headers, how to place the pointers in the intermediate nodes, what are high keys, what are overflow pages, how do you rebalance the B tree, and other sorts of tricks you can do in B tree. There are 2 recommended sources or literatures at the end of the chapter that I found interesting. The first book is called Modern B Tree Techniques, and this one is also recommended by Andy, Professor Andy from the CMU course I mentioned. It's a pretty comprehensive manual that talks about everything from the research area to industry implementations, all the tricks you can do to improve your B tree in a database, and that kind of everything bundled into a nice manual book. And I read kind of the first 2 chapters, and I think the language is pretty clear and the explanations are vivid. So highly recommend this book if you want to get into the details of the B tree. The second book is called Disk-Based Algorithms for Big Data. And this book, I believe it's published after 2010. So it's pretty relevant book, but I haven't read about it. So if anyone have seen this book or have any comments, feel free to say it. And okay, so given that, chapter 3, we talks about how we can lay out different data structures in disk. And chapter 2 and chapter 4, we talks about how do you implement indices using B tree. Now we are kind of in this stage that we understand how database stores things on disks, but we haven't introduced you the most critical parts of the databases, which is transaction. I feel like everyone has heard about transactions or use it. It's just the most famous thing in the database field. So what is a transaction? It represents a sequence of read-write operations, and you combine them into one single step that you want the database to perform. And the most famous example for explaining transactions are, you want to transfer some money from one bank account to another bank account. So you will say something like, begin this transaction, and if let's say Bob wants to transfer $100 to Alice, you say you minus $100 from Bob's account, and you add $100 to Alice's account, and then you commit this transaction. So the transaction in the database will need to satisfy some properties to be able to perform correctly and efficiently. And I will touch them briefly in the next slide. So to be able to implement this concept of transactions, we have more components to learn that are actually implemented in the database. So those are buffer management, log management, and recovery. And we need to learn all of them to be able to understand the database transactions. All right, so I just talked about the money transfer example. Here is a PostgreSQL transaction sample that starts a transaction, updates some account, and roll back the transaction. So there are three special syntax that introduce in transaction. One is begin, one is commit, and another one is rollback. So commit in transaction means that if you hit commit at that stage, everything included in this transaction, everything being modified should be persisted in the storage. If you roll back a transaction, it means that everything that being modified by this transaction should be rolled back to the previous state. And the reason we need rollback is because it might fail some constraints set by the database, by the schemas. And in this example, I can think of, if the balance goes below 0 in your bank account, that doesn't really make sense. So at this stage, you might need to roll back your transaction. Every single implementation of transactions need to satisfy some properties. And it's given by an acronym called ACID. ACID is composed of the first letters for each word: atomicity, consistency, isolation, and durability. So whenever you talked about transactional databases, people always say ACID. And there is a kind of reversed way, or the other, a word that describes non-ACID is called base. But we are not going to talk about base today. We are talking about ACID. So what is atomicity? Atomicity is, it's also called all or nothing. It means that when I execute a transaction and in the middle of the transaction, the database failed or crashed, I have to make sure that from a user perspective, it doesn't expose any partial failures in the transaction. So either every operation in the transaction all committed, or none of them are committed. That's the phrase "or nothing" means. So atomicity is related to crash recovery algorithms. The second term, consistency, it's probably the most vaguely defined term in ACID. I feel like the academic who comes up with the word ACID want to throw in a consistency to make this word, memorable. So consistency means that if you have a valid transaction, before the transaction, if your database is consistent, then executing this transaction should not make your database not consistent. So if you are from one consistent state and you execute your transaction, you should go to the next consistent state. And what is consistent in this general sense, you can think of those application-specific constraints like primary key constraint or foreign key constraint. Those can be regarded as consistency. The third word is isolation. And I feel like people talked about isolation the most because isolation deals with concurrency. If you have concurrent transactions, if you are executing concurrent transactions in the database, you want some protections to isolate each transaction so that they don't interleave with each other. Because I said we have a abort syntax in transaction. So it means that if the transaction is executing concurrently with other transactions, if the other transaction can see this one, but this one it's aborted eventually, that means we have to prevent the other transaction being affected by this abortion operation. And that's where the word serializability comes in. Serializability means that you want your transactions to be eventually the result of your execution transaction should be serializable, meaning one transaction should be appear the next. You can put every transaction as a dot in the timeline. But having serializability is a great thing in databases, but it comes with a great price. It has a huge performance overhead. That's the reason why so many databases nowadays are kind of implementing a weaker notion of isolations. And that gives a different isolation levels. I think we'll talk about this next time when we talk about concurrency control algorithms. The first term is called durability. Durability, it's pretty easy to understand. If a transaction commits, all of the data that is being modified by this transaction should be persistent. It means that if you think about in a lower level, it means that if your transaction has modified so many data pages, but it hasn't flushed into this database, durability means that you have to eventually flush them into the disk so that they are persist. So there is a kind of assumption that your disks are persistent. And to make your database persistent, you have to flush everything you modify into your disk. So durability is also related to crash recovery, because if you are executing a transaction and in the middle of that process, you crashed, the system crashed. So you have to either roll back the transaction to the previous state, or if the transaction is committed, but the data being modified is not flushed to disk, so you have to redo everything the transaction has done during the recovery stage. So atomicity and durability are kind of related to this crash recovery algorithms we'll talk about later. Just keep that in mind. Let me just pause here for a second, because this is very important notion to understand in database transactions. Does anyone have any questions regarding the notion of asset? Okay, great. Let's move on. So I briefly mentioned that to be able to implement transactions, we need more components. And the book lists several of them. The first one is called Transaction Manager, and there are Log Manager, there are Page Cache, and finally Log Manager. I think we also briefly touched one of them in the first meetup. So now a question for you guys. Can you describe the purpose for each of these components? Let's start with the transaction manager. Can someone describe what a transaction manager is? What's the purpose? What does it do? Anyone want to give a try?
Kinds of like handling different transactions and decide which should be abroad, which should be commit, and redo or undo any changes for transactions.
Mm-hmm. Do you think it's the transaction manager's job to redo and undo a transaction? That part is actually, I'm not too sure about this part. But a transaction manager basically manages schedules and tracks transactions and their individual steps. But I don't know if it's playing a role in recovery stage.
I'm not sure either. So
yeah, okay. I guess we'll leave this question here, and then later if we can find out the answer. Serge, are you going to say anything?
I was planning to.
Sure.
The role that transaction manager plays in recovery is just assigning transaction IDs, which is essentially a unique number per transaction. Each transaction is identified by a unique number. That's all. Every time you write something, you write, here's the data and here's the transaction in which it happened. And that's the only thing that transaction manager does at this moment. The rest is done by log manager. And the second comment is the transaction manager actually does not decide whether to commit a rollback. The client does. The client says rollback, rollback. The other situation is where the system either crashes or violates some of the rules. For instance, you wanted to insert ABC into a numerical column. This transaction cannot be committed. It depends on the system. Sometimes it's up to you to decide what you want to do. But really, the only thing you can do is roll back, correct? Because it cannot be committed. So what else can you do?
I think the transaction manager does control the rollback, because if something failed, and the transaction manager will roll back regardless what a client does.
Yes, we are just talking about two different definitions of deciding how to roll back. The transaction manager, yes, implements the rollback. You tell it, I want to roll back, and transaction manager says, yes, sir. You know what it does? It adds one little record into the logs. This transaction, when we have the number, has been rolled back. That's it.
Got it. Okay. Thank you so much, Serge, for answering the question. So let's move to the log manager. I think you briefly mentioned what log manager does. I think it's pretty obvious right now. It's log manager. It's deciding to give logs to those concurrent transactions. Can someone describe what is a page cache? It's also called buffer pool. I think the Alex likes to use page cache in this book.
I think page cache is something we are using to read the data we want into the memory. For example, if we have limited memory, then we need to read page by page.
So it's the job of a page cache to read something from this to memory.
Yeah,
and manage that.
Also remove something out of the cache, out of the memory if we don't have enough space and we need to read more data into the memory.
Great, yeah. So that's the eviction policy, which we'll talk about later. Great. So the last one is the log manager. I would just say what it does. I think in the book, it says that the log manager is responsible for holding a history of operations. So they call it a log or write-ahead log. And this history of operations are applied to the cached page, but haven't been synchronized with the persistent storage yet. So that's their job. All right. So let's move on. So now let's talk about buffer pool or page cache or buffer management. In every database, we are talking about disk-oriented databases. It uses kind of two main medias to store data. And one obviously is the disk, and another one is the main memory. The reason they want to use main memory for storing data is because they want to have a higher performance in accessing those data. So this is a picture that I extract from the book that talks about how a B tree really looks like if it's visualized in a way that the buffer pool points to the node in the B tree. And the buffer pool also has a table that maps each buffer page to the page in disk. So I found this picture is pretty cool and explains buffer pool as this intermediate layer that just kind of just serving as a cache to speed things up. And in terms of the semantics of the buffer pool, I just quote from the book, the page cache abstracts these accesses and decouples logical write operations from the physical ones. And this is pretty interesting because what is logical write operation? It's from the user perspective, I write something to the database and it commits. So to my mind, my data has been written, but from a database perspective, it could be written to the disk, but it could still be in the memory and later flush into the disk. So that's the physical write operations, whether or not it's actually persistent in the disk. So this two can be decoupled, and that's where the page cache fits into. It has several terms related to page cache I want to talk about, briefly mention them. One is called the reference cache. And reference cache is basically if you read something from the disk into the memory, and this cache is being accessed, and we call it it's being referenced. You can also pin a cache in the buffer pool, meaning that it won't be evicted very soon by the eviction algorithm. You just pin it in there, so you want to keep it a long time. And there is also a dirty flag in every cache page. The dirty flag tells that if the cache has been modified or not. If it's dirty, it means it's being modified, and it means eventually it needs to be flushed into the disk. If it's not dirty, it means that the page hasn't been modified, and so there is no meaning to flush it to the disk because those two are synchronized. And whenever we talked about caching, there is always a assumption that cache is that it's the small thing and this is the big thing. So eventually you are running out of space in the main memory, and that's where you need to evict something from your cache to leave some space for the new thing coming. And whenever we implement cache evictions, the book talks about there are always a trade-off between several objectives. I'm not going to read all of them, but the first three objectives are kind of want to speed up your cache evictions. And the last two objectives are related to correctness and durability. So you can't lose durability to make your cache eviction super performant. And that's where you need to think about how you can do this correctly. So the first most intuitive algorithm is called FIFO page replacement or page eviction algorithm. And FIFO here means first in, first out. You can think of just as a queue. It maintains a queue of page IDs in their insertion order. And whenever the queue is full, whenever you have a new page added to the queue, you add to the tail. And whenever the queue is full, you take the page out of the queue from the head of the queue. So this algorithm, it's pretty simple to understand, but it has some significant drawbacks. So I have a question here. Can you think of any kind of pros and cons for this simple page replacement algorithm? Like if you are going to implement a buffer pool page eviction, why would you choose this one versus the others you can think of? Does anyone want to give a try? I will give one pro. It's super easy to implement and super easy to understand and reason about. Suma said the con is if the page is popular, you will get evicted. Yeah, so it doesn't take into the consideration that there might be some locality properties in page accessing. And if one page is being accessed very frequently, but if we access another one, it might evict out the most frequent page. And that's one of the drawbacks, yes. The book talks about another interesting idea. It's called the Pallades anomaly. If you think about it, there is a misconception that if we add more memory, there definitely will be less page eviction faults. Page eviction faults meaning that you are evicting the pages that actually could be accessed more often. And in the late 1960s, I think Pallades discovered that's not the case. And it's actually unbounded. So whenever you increase the number of page limits, the number of evictions could be even higher. And the difference between number of pages and the number of evictions can be unbounded. So if you implement your page replacement algorithm in FIFO order, it doesn't guarantee that if you add more memories, you will get less evictions. That's the essential idea of Pallades anomaly. So I paste a kind of example from Wikipedia that shows if you add more memory, you actually have more evictions. So let's take a look at this picture together. I have this pointer stuff here. So the first one has three slots for the memory. So it's using FIFO order. So if you are accessing 3 to 1, you get 3 evictions because currently in the memory there are no cache. So you need to add 3 to 1 into the cache, and that makes your cache full. And if you access 0, you have to evict 3. And then you access 3, you have to evict 2. And then you access 2, you have to evict 1. And it goes like this. And eventually, the only hits are 4, 4, and 0. In this case, 3 hits. But if you add memory, one more slot in the memory, now you get 4 slots. So you can store 4 things in your memory. But it doesn't make this better. You have only 2 hits in this case with the exact page requests. So above one has 3 hits. This one only have 2 hits. So adding more memory means your performance is even worse in this case, which I found to be very, very unintuitive. But this thing exists, so you need to be aware of it. I think Pallades anomaly in that paper describes if the eviction algorithm is not optimal, this will always happen. And so now we are going to look at some optimal eviction algorithms. The first one is called LRU, page replacement, standing for least recently used. It still maintains a queue of page IDs in their insertion order, and it adds new pages to the tail of the queue. But the only difference between LRU and the FIFO page replacement is that LRU keeps updating the page if it has repeated access. So whenever a page being accessed again, you will place the page back to the tail, kind of telling that this page is the newly accessed one. So it's the most recently used page. And I only evict the least recently used page. So those pages on the head of the queue. So now if the queue is full, we still take page from the head of the queue. Now the question is, compare LRU to FIFO. What's the pros and the cons? Again, for the con, obviously LRU is going to have a worse performance than the FIFO page replacement because you have to actively tracking or shuffling the pages, right? You have to place page from one position to the tail of the queue. And that takes extra complexity to do that. Someone just name one pro for this algorithm.
It could be like the most frequently accessed page could be at the top. Like in FIFO, even if we were using a page very much frequently, it was still it still had the possibility of being evicted. But here, if you are using it very frequently, it will not be evicted soon.
Yeah, right. So what you said is that compared to FIFO, LRU has less probability of evicting pages if the page is accessed more frequently. So it follows the locality property very well. All right, so I mentioned that this LRU page replacement algorithm has some performance issues. There are some alternatives. There is a one called 2Q, and there's another one called LRUK, which are pretty interesting. I haven't read about them yet, so I don't know what exactly they achieve. But from what I heard, the LRUK algorithm solves a problem called sequential flooding. So the problem is very interesting. Sequential flooding means that if you have a query that comes in that want to sequentially scan the keys from left to right, say I scan from A to Z, all of the 26 letters, and say my memory slot only have like 10 slots. So every single access from A to Z is going to be a miss because you can only put 10 things in the memory, and the next letter is never seen in the memory. So you have to evict A, and then evict B, and then evict C. And say we have another sequential scanning comes in that scans from A to Z. So since you already evicted A, the most front letters, it means every single sequential scanning is going to get misses. So that's pretty bad for LRU. So that's where the LRUK page replacement algorithm tries to solve. If you are familiar, if you are curious to learn them, feel free to look into those papers I paste here. If the database design cares more about efficiency than precisions, there is another famous algorithm called clock. Clock page replacement algorithm, it's pretty compact and it's cache friendly, and it's very concurrent friendly. So what does it do is that every page has a reference bit. The bit can be either 0 or 1. And whenever the page is accessed, it sets the bit into 1. No matter what the bit is, it just set to 1. And all of the pages are organized into a circular buffer. So that's where the clock means it's a circle thing. And if the buffer is full, then you have to evict something, right? And so you start your eviction algorithm, and the eviction algorithm goes by sweeping the pointers in this circular buffer from, I guess, 12 o'clock all the way back to 12 o'clock. So that's where the clock name comes in. And upon a sweeping, if the page bit is set to 1, meaning that the page has been accessed, you set back to 0. And if the page has not been accessed, you evict that page. That's where you can find extra space. And if everything is set to 1, right, so you have to go around the clock from 12 o'clock to back to the 12 o'clock, and you set everything to 0. And when you go back to 12 o'clock, that's the one you are going to evict. So clock page algorithm, it's kind of like approximate algorithm for LRU, and it's much more efficient because you only need to change a bit from 0 to 1, and the checking bits are pretty, well, in my mind, it's faster than LRU, and you don't have to keep actual timestamps into your page. You only need to keep 1 bit. But as I said, clock is a approximate algorithm. Can anyone think of an example that, you know, clock is incorrect in the sense that it evicts the most recently used page? Because this will never happen in LRU, but it could be happen in this clock algorithm. This is a nice exercise to Does anyone want to give a try? So let's say, I'm just going to draw on the slide. Let's say we have 3 slots in the memory. And let's say at the very beginning, we access A, B, C. So the 3 slots are being taken, and all of them are set to 1 because they have been accessed. Now let's say we want to access a if we want to access D, that means we have to evict something from this circular buffer, right? So although I draw them in a linear way, but you can think of the C as going back to A here. So when we go around the clock, we have to set everything to 0. All right. And the next thing, it says it's A and it's being set to 0. So if it says 0, we want to evict that. So we evict A and we set it to D and we set back to 1. Right? Does it make sense?
Do you set it to zeros like at each each cycle of the clock? It seems you set all the 1s to 0 at the same time.
I set 1 to 0 is because according to this description, right, I check if the page bit is 1. If yes, I set to 0. So at the very beginning, everything is 1, I set them to 0.
Okay, but when you set the A to 0, but at the same time, you also set a B to 0 too, because it's 1.
Mm-hmm. Yeah.
So one sweep actually set all the pages to 0.
Yep.
Okay.
Yep. Now,
Afraid not.
So what did you say, Serge?
Afraid not. It doesn't set everything to 0 at once. It goes 1 by 1.
Yeah, it goes like a clock, like a pointer.
Yeah. So the sequence he described is actually A, B, C, right?
Mm-hmm.
Then replace it with D. Then B is not used, right? We change it to 0. So the pathologically bad sequence will be A, B, C. Could you please write it down? Like A, B, C, then A many times, and then D. It's going to override A, but A is very popular. The only difference, we don't see it. We only have numbers A, 1 and 0, popular, not popular. We don't differentiate how popular.
Yeah, that's the example, right? We access A many times, but now
it's still 1.
It's still 1. Now we access D. We are going to set A to 0, B to 0, C to 0, and go back to A, and we evict A. Yeah. So this is the case where it evicts A, the most recently used one.
Right, because it cannot differentiate between a very useful page and page which was slightly useful. We assigned it 1.
Mm-hmm.
So 1 is no different from 10,000.
Exactly. Does anyone?
I don't understand. And so this A can be repeated, assuming you have some kind of data structure to store this one. So actually, you can actually repeat the same page in the slots.
No. That's a sequence shows a request, which page you want.
Okay.
You want A, then you want B, then you want C, and
Sure.
then you want A many times.
Yeah, let me make this clear so that there is no confusion what we are talking about here. So A, B, C, A, D, this is the sequence of requests coming, right?
Sure.
So the time goes from left to right. So let's say we have 3 slots. Now let me draw it in this way. 3 slots. It goes here, here, here. That's like a clock. So the first A, we are going to take this space and set to 1. Now B comes in with here, we go here and set to 1. C come here, we set to 1. And that actually filled up my memory. I don't have any free slots anymore. So the next A comes in, I go to here, I found it. So I still have 1 here set. And the same for the next A, the same for all of those A's, I still keep 1 here because I'm using 1 bit. So it can only be 0 and 1. I can't change this to 2. Now D comes in. According to this algorithm, I have to set A to 0, right? And then I go to the next one. I set B to 0. I go to the next one. I set C to 0. I go to the next one. Now I'm seeing a 0 here. According to this algorithm, I have to evict this one. So I evict A and replace with D.
Okay.
Right. So that's the bad part of this algorithm because A is the most recently accessed element, but it replaced it. But it's fast, so that's why people like it.
I have a question here.
Mm-hmm.
So by the time when A is accessed multiple times, why B and C are not evicted?
Because it finds A here, right? If A, it's being accessed, so if you...
So do you mean that the pointer will stop spinning through the other slots?
Yeah, the pointer will just stuck here.
Okay, I see.
Yep. Oh, if you can find A here, yeah, that's some detail I'm not quite sure. If you find A here, say if the pointer is here, but you still want to access, okay. Let me just erase.
Yeah, because for now it looks like A is being referenced. If a page is being referenced, it cannot be evicted, if that makes sense. But
Right.
I'm just wondering why B and C are not evicted.
If you can find it in the memory, then you don't need to evict. If you can't find it, you have to evict. That's where the algorithm comes in. That's where you need to rotate the pointers to set everything to set the bits to 0 if it's 1 or evict it.
Yeah, right now it looks like as long as the page is found in the clock, then the pointer will stop there. It doesn't go through the other slot in the clock.
Yeah, I agree.
So when the A is set to A is set to 1, then you request A again. Do you still keep the bit as 1, or are you gonna set the 1 to 0?
You don't set it to 0. You still keep it as 1.
Okay.
So the algorithm is whenever the page is accessed, you set to 1. No matter it's 0 or 1, you always set to 1.
Okay.
I have a question. Like, can we do one thing here, like the page which is being most frequently used? Can we just pin it like in other algorithm? Like we have this pinning.
Wait, sorry, can you repeat your question?
So I was asking, like, can we do one thing like the page which is being most frequently used? Can we just pin it?
If a
Pinning the
page
page.
is most frequently used, can we pin it? Yeah, that's actually the next algorithm I'm going to talk about. Good question. So there is another algorithm called LFU page replacement that stands for the least frequently used page replacement algorithm. So LRU is the least recently used. And this one is actually tracking the frequency of your pages such that you only evict the least frequently used pages. I don't know if this description makes sense. So basically you have a counter in the page. Whenever you access it, you increment the counter. And if you want to evict some page, you scan through all of the pages and you find the smallest counter value and you evict that. So yeah, that's the high level of this algorithm. And in the book, they talked about a specific implementation called Tiny LFU. It has this 3-stage emission, probation, and protected. But I think for us, I don't think we need to go into the details of this one. Just to understand the general concept of how LFU works is enough.
When do you decrement the counter? Because you're talking about every time it's accessed, we increment the counter. When this counter is decremented? There is no, we don't need to decrement, right? Or if you specify a specific time range, say, I don't know, I'm just guessing here. Say in the last 5 seconds was the most frequently used one. And after 5 seconds, you reset to 0. Okay. Yes, somehow you just, because you only evict the page when the counter is 0. So yeah, but in practice, I don't know if anyone done that because that's some actual complexity going on. Counter, that's per page, right? Each page has its own counters, right? Right, yes. Okay. Implementing LFU leak code 460. I remember that's a hard question, right?
Correct. LRU is simple question. LFU is actually hard. So you don't decrement, there is no need. You just prune the smallest number.
Mm-hmm. I imagine you need to use some priority queue. And
actually it can be done in O1.
In what?
O1. Yes.
Oh.
You can use priority queue. You can do it in O1. I'm not sure if you can do it in the database structure though, because it's a linked structure.
Yeah.
So it's a circular linked list sitting on the side of a circular linked list. At least in my implementation, I played with that. It took me a couple hours. It's 100 lines of code.
Yeah,
which is a lot for lead code.
Don't ask this one in the interview.
But you don't need the counter, right? If the way the implementation, like a linked list, you maybe need hash, but you don't really need a counter for that.
I need a counter. It's just it's not a usual linked list. It's a linked structure, but it's not a linked list literally. For the reason is that if you have a normal linked list, finding something inside it cannot be all one.
Mm. So you also need a hash map or something.
Well, kind of.
Yeah.
You have a linked list in which one element is always 1, the second one is always 2, and each one contains a set. Mm-hmm. So if you want to increment the value from 2 to 3, you get to the element which named 2, and you know that you have to push it to the next element. So you have to take it on a set that's sitting on element 2 and push it to the element sits on, to the set that sits on element 3, which can be done in O1. And if you want to find the element where to start, yes, you need an index to it.
Yeah.
But overall, it's a pretty complex structure.
It is. Yeah. Thanks.
Try to play it and compare it to implementing LRU, and you will see how hard it is. Try hard to implement it all one time. It can be done.
Great. Thanks for sharing. So that's a
in the real database, and it's not always need the counter, but it's still like somehow it's a combination of LFU and LRU. Take my SQL as an instance. That my SQL has this like two cache list, and both cache lists are using LRU. But just like this this diagram, that for example, the protected queue can use LRU, and the frequency filter queue can also use LRU. But there has a ratio that some of the LRU are protected, and some of the LRU are just like easy to vanish. So in like a real database, that it's somehow sometimes using the combination like of LFU and LRU. It's kind of like similar to the like a generation in the JVM, that there's always a pattern that some of the object or some of the buffer will be used for a long time, even though sometimes it's not so frequency. And but we need to make it in the buffer pool. And but also some of the short-lived object or buffer that will be changed a lot.
Yeah. Thanks. I just found that this one is so complex to actually implement. But yeah, the book mentions tiny LFU. If you're interested, you should go take a look at it, how it's being done. I'm assuming it's open source, right?
So is this one, like in general, is a better algorithm compared with the other one, or?
Yeah, well, intuitively, this one counts the frequency of the page, right? So yeah, it explores the locality very well. The most recently used, as you see, it's just putting elements to the tail of the queue, which is not super precise. But it depends on scenarios. I don't know if this one has any better performance than LRU if we are going to do sequential scans, because everything is being accessed once. All right, so that's enough of page replacement policy. Let's move on to recovery. So recovery, it's very interesting. And let's talk about the write-ahead log first. I believe everyone has heard about write-ahead log. So why do we need this recovery algorithm? Every implementation of databases has composed of so many components, and each component may fail at any time. And if the component failed, it could either be interrupt the transaction in the middle, or the whole database system has to shut down and restart. And at this moment, if you want to make sure you still have atomicity and durability, you need to do some special handling in the databases. And that's where the write-ahead log comes in. Write-ahead log is a append-only disk resident structure, and it's particularly useful for recovery, and particularly used for database crash recovery and transaction recovery. And high-level idea is that every single modification operation needs to be logged into this write-ahead log before the contents of the page can be modified or can be flushed to the disk. So that's where the write-ahead means. It's being used to reconstruct some of the data structures during recovery stage, and it's very important in transaction processing. We'll revisit this one later. So as I said, write-ahead log, it's a append-only data structure. So what do we append to this data structure? I found a kind of description from another college course that shows what's inside of a log. So a log is composed of different records, and each record contains a LSN. LSN means log sequence number. It's usually a timestamp, meaning that it's unique and it's monotonically increasing. And every record just can be either the operation that modifies some pages, or it can be a checkpoint message, or it can be a transaction commit message. So this record has multiple purposes. There is also a thing called compensation log records, and they are supposed to be used as undo logs. I'm not too familiar with this compensation log records. If anyone's familiar with this one, you can comment on this. And one of the problems for write-ahead log is that it keeps increasing in size, right? Because every single write request comes in, you have to append something into your WAL. So there is a process called trimming the write-ahead log. It's called the checkpoint. And there are checkpoints. Okay, I will talk about fuzzy checkpoints later. Although I put in this slide, but let's talk about checkpoint first. Whenever you start a checkpoint, you just append some special message called checkpoint into your write-ahead log. And I took a screenshot from the CMU course that shows an example of a write-ahead log. Here you can see it has 3 transactions, T1, T2, T3, and it record the beginning of a transaction, when the transaction commits, and what's the operation inside of a transaction. So in this case, you can see eventually the database crashes, and now you need to do recovery. And the checkpoint is placed between the beginning of transaction 3 and the commit of transaction 2. So everything that commits before a checkpoint, you don't have to worry about it because it's already persists in the checkpoint. You can just start with this checkpoint and you have T1 already in here. So you don't have to do anything about it. But for T2, it's already begin and it's committed before the crash, but it's not being written to the checkpoint. So for T2, you have to redo everything that's in the transaction T2. For transaction 3, it began, but it hasn't committed before the crash. So you have to undo everything that transaction 3 does. So here it's a clear example of the differences between redo action and undo action. Okay. I will pause a second here for you to ask questions. I know this is a little bit hard to grasp if it's the first time you see it.
What happens if you fail to write to the commit log, like the write-ahead log? You in that case, do you just lose your data?
In that case, so as I said, you have to write to the write-ahead log first before you can commit your transaction. Well, I guess this is wrong. You have to write something into the write-ahead log before you can persist it into the storage. So if the first prerequisite step failed, it means that you haven't persist to disk yet. So in that case, it just being regarded as failed, and it doesn't impact the durability of the database.
Okay, thank you.
Yep. All right, so let's talk about undo and redo. So from that example, if you apply a redo action, you kind of produce from a before image of the database to an after image. If you apply an undo, you actually go back in time, right? You go from after image and to a before image. And there are 2 notions of log. One is called physical log, and another one is called logical log. the physical log is actually, you can think about just like a git diff. It actually stores the differences in bytes. What's the state before you execute this operation, and what's the state after? And it requires the entire page to be logged into this physical log. And it's usually used as to perform a redo action. The logical log stores kind of high-level operations, like if I modify something here, and it just store a modify operation, and it doesn't store the actual bytes, the modified bytes into the log. And so the logical log can be much more compact than the physical log. It's much smaller. So it's usually being used to perform the undo operations to improve concurrency and performances. Here is another nice example that I found from the CMU course. It has a physical log example, or logical log, and kind of they thought a combination of this to called physiological log, which is a funny name. So the physical log here, you can see it logs the table, the page, the offset, what's the bytes before and what's the byte after. In the logical log, it just logs the high-level query operations. It has a update, a set, and where my ID is. Let's not talk about this physiological example here, because I don't know what's the real differences here. I guess the only difference is that it doesn't have a offset. But in that course, Professor Andy said physiological log is the most commonly used one in the real database implementations, because both physical and the logical have their drawbacks. All right, and now we are going to introduce more terms. That's the steal and force policies, and those are related in the buffer management implementations. So a steal policy means that it allows the buffer pool to flush a page modified by a uncommitted transactions. So to the contrary, non-steal policy means that it does not allow flushing any content to disk if the transaction hasn't been committed yet. A force policy means that the buffer pool requires all the dirty pages to be flushed on disk before commits. And the I have a typo here. It's non-force policy. It's the reverse way. It allows the transaction to commit even if some dirty pages are not flushed. So those two definitions are kind of diagonal if you think about it. And I found this nice picture that shows the relationships between steal policy and force policy. So if you have a non-steal and a force policy, the performance is going to be the slowest. But that's the most constrained environment, because you can't steal and you have to force everything, every dirty page to be flushed before you commit. And that means it's much easier to do recovery algorithm within this environment. So you don't need a redo and you don't need undo. If you are using a steal and no force policy, then it's the fattest performance you can ever have in the recovery algorithm, but you need undo and redo to ensure atomicity and durability. Does anyone have any questions here? Confused about like what steal, force are and why it's why we need undo, redo? Okay, let's move on. So
I got
now,
a quick question.
Okay.
Why do you have a steal policy? Because it seems it's a committee that it's going to write the uncommitted data, right? That's a steal policy.
Why do we need a steal policy? Can you repeat your reason?
Yeah, because in the book it's talking about it's allowing the flushing a page modified by the transaction, even though it's not committed. But why, I just quite understand, like, why do you want to flush uncommitted transactions? Do you, flushing here, does that mean like a write to the persistent database? It is persistence disk, or flushing just like a
write to the persistent storage? I can think of one simple reason for why we need steal policy. If you don't flush them during the transaction, if the transaction is super long, it has so many modifications, then you have to flush everything once you commit at that later stage, right? And that might have some performance overhead.
But if you don't want the commit, then transaction, how do you gonna roll back? Because seems you already have flushes.
Yeah, that's where this picture shows, right? If you have a steal policy, you must have a undo log for it to roll back.
Oh, okay, got it. Thank you.
Yeah. So if you have a no force policy, you must have a redo log for it to be durable. Okay, so this question.
Sorry, I have one question. Could you go back? Yeah. So for the undo, the definition for the undo, I think it's rollback updates for uncommitted transaction. That's when we need to roll back. We need to roll back, right, to apply the undo log. Why, if we have committed, why do we
roll back updates to force pages for committed transactions? But you are right. The purpose of undo is to undo everything that is being done by uncommitted transactions.
Yeah, maybe it's not forced page, it's stealed page, steal page, then committed transaction. Yeah, that's just my understanding.
Yeah. I'm trying to think if the words here are correct. Forced pages for committed transactions. Yeah, you are right. Maybe I have a typo here. It's for uncommitted transactions. And the redo is for committed transactions. Right. Thanks. All right. So now let's talk about the recovery algorithm. And the book describes one called ARIS. And ARIS is a steal no force recovery algorithm. So that's actually corresponding to this one, steal no force. And that means it has a undo log and a redo log. ARIS uses a physical redo log to improve the performance during recovery, and it uses a logical undo log to improve concurrency. And the reason they need a redo log, we discussed just a while back. The reason we need a redo log is because we want to replay the committed operations in the committed transactions. And the reason we need undo log is because we want to roll back any operations done by uncommitted transactions during the recovery stage. And to implement redo log and undo log, it uses the write ahead log protocol. And the write ahead log basically persists every history of all the operations. So you can go either left or go right. So the write ahead log can implement both redo log and undo log. And it uses the fuzzy checkpointing. I think I've skipped the definition of fuzzy checkpointing. So I mentioned checkpoint. The purpose of checkpoint is to trim the write ahead log so that it doesn't grow unbounded, it doesn't grow too big. But in order to trim the write ahead log, the most naive implementation is that you have to pass every single operations in the database. So now you can take a snapshot of your write ahead log, because they can be concurrent operations coming in when you are taking a snapshot of the write ahead log. But fuzzy checkpointing is a way that you can still make your database function while you are taking a snapshot. The implementation details of fuzzy checkpointing, it's probably not too important here. If anyone's curious, we can talk about this later. But just remember, fuzzy checkpointing is the one that you don't have to pass the database in order to take a snapshot of your write-ahead log. And errors are split into 3 phases. The first one is called the analysis phase. The second one is called redo phase, and the third one is called undo phase. In the analysis phase, the purpose is to identify all of the dirty pages. Those pages are modified by the operations. And they also collect a list of in-progress transactions. Those transactions haven't been done yet. So given dirty pages and in-progress transactions, we enter the second phase called the redo phase. Redo phase are going to repeat the history up to the point of a crash. And so it looks for every incomplete and committed transactions and basically look their redo log and start replaying everything in the log so that they can reproduce the image at the point of the crash. So the third phase, called undo phase, those are to roll back everything that has been done by uncommitted transactions and restore the database to the latest consistent state. So the redo phase is to guarantee you have durability because your transaction is committed, so they have to be persist. And if you don't persist them, you lost durability. So you have to replay everything to make sure you have durability in the database. In the undo phase, it's going to make sure you need your database guarantees atomicity. Atomicity is all or nothing, as I explained before. You don't want to have partial result exposed to the user. And those incompleted transactions already have pages being flushed into the disk, and you have to roll back everything because errors is a still no force policy. So it could be the case that your transaction hasn't been completed, but it has some effects on the disks. So that's where you need to roll back them. And it guarantees atomicity. Hopefully the description here is clear. Does anyone have questions regarding the 3 phases and why we need them? Great. So that kind of concludes the everything I want to talk about today. It's actually just the first half of this chapter, which is crazy. Next time, we are going to talk about concurrency control algorithms. Especially, we are going to talk about different isolation levels and the conflicts between read-write, write-read, and write-write, and how can we come up with algorithms to deal with those anomalies. And the algorithms we are going to talk about are optimistic concurrency control and pessimistic concurrency control. And in optimistic one, we are going to have multi-version concurrency control. In pessimistic one, we are going to have 2-phase locking. So that's everything we are going to talk about next time. And there are some references that are relevant to today's slides. I took some ideas from several college courses. And there is the errors paper, which is 68 pages long. And I don't intend to read it. It's just too long for me. All right. All right, thanks everyone. Do we have any questions or things want to discuss about this chapter? Let me take a look at the
Thank you.
problem. let me take a look at the pre-meetup questions. See if we get any. Yeah, we don't have any questions. Nice. Okay, then we will see you next time on Friday at the same time, 5 p.m. And please read chapter 5. All right, see you then. Thanks for joining.
Thank you.
Thank you.
Bye-bye.
Thank you.